charge this while I'm away. Do my timer. On alarm. Oh shoot. Ready for that. I gotta go to iMovie. Let's see. One hour. Let's do 35 minutes. We can close that out. Done. All right, let me share my screen. All right, greetings YouTube, Beautiful Mind here. And so the following, basically we had six questions incoming from calculus, and so this is just one long video for all 6 questions. A lot of these questions are centered around like optimization in calculus. So the underlying theme is like, okay, you have a word problem that you have to organize. You get some function, you get some function that kind of describes the situation, like cost in terms of X or something like that. And then we want to either minimize the cost or maximize profit, things of that nature. And so all the questions have some structure like that. In order to minimize, what we do is take the derivative, and then we use the first derivative test to find our critical numbers. Once we have our critical numbers, we use the first derivative test to show that it's either a local max or a local min. That's pretty much the theme for most of these questions, okay? All right, so without further ado, let's get the party started. All right. All right, greetings YouTube, Beautiful Mind here. We have this question that comes from calculus. Let me zoom in, and I'm just going to read it off. Give me a moment. It's not letting me zoom like I would like. Okay, let's see if this is better. All right. Okay. So it says, consider the following statement. Of all the rectangles with a given area, the one with the smallest perimeter is a square. The following is a proposed proof for the given statement. Let the rectangle have sides x and y in area A, so that the area of a square is going to be x times y, which is length times width. And so if we solve for A, we get y equals A over x. The problem is to maximize the perimeter. P of the perimeter of a rectangle is 2x plus 2y. So then if we substitute y in for x, we get 2x plus 2a over x. So then if we take the derivative for step 3 with respect to x, the derivative of 2x is just 2. That 2a, you just treat it like a constant. So that's really some number over x. So then that derivative with respect to x is going to be negative 2a over x squared. So then if we, do algebra, get a common denominator, it simplifies down to 2 times x squared minus a.
Then step 4 says, so the critical number is x equals a. Step 5, since p prime is strictly less than 0, for 0 strictly less than x, strictly less than the square root of a, and p prime of x is strictly greater than 0 for x is greater than the square root of a. There's an absolute minimum at x equals the square root of a, and then the size of the rectangle is square root of a, and a over the square root of a equals the square root of a, so the rectangle is a square. We're asked to identify the errors in the proof and select all that apply. So let me see. When I went through this one earlier, so of these 3 that are checked, I got that the first one checked is correct, the second one checked is incorrect, and the third one checked is correct. So that when I did it earlier, that's what I got. It said the second one says that the second sentence should say minimize instead of maximize, and I think that's correct because our goal is we want to minimize the perimeter. So in that second step, we wanted to minimize perimeter. And then that third tick mark says, in the fourth sentence, the critical number is incorrect. It should be x equals the square root of a instead of x equals a. And I think that's correct as well. The critical number should be x equals the square root of a. So critical number from step 3 are going to be any x that makes either the numerator 0 or the equation undefined. A critical number should also be x equals 0, but maybe in the context of the problem, that's why they're not considering that one. If it marks it wrong, then that one might be wrong as well, because that might be missing a critical number. But I think the x equals 0 doesn't make sense in the context of the problem, so that one might be thrown out. Okay, so yeah, at first glance, it should be, of the 3 that are checked, I got 1, 2, 3, like keep the first, get rid of the second, and keep the third. If that doesn't work, then just keep the first one. Okay, so that was part A, and then part B here. Of all the rectangles with a given perimeter, the one with the greatest area in the square, the greatest area is a square. The following is a proposed proof. I'm not going to read through this one. But when I worked it earlier, and you can pause and kind of make your way through it, and you basically kind of have to go line by line until you find an error. This one I only found one error. It says the fourth sentence should say absolute max instead of absolute min, and that was the one that I found when I read through it earlier. Okay, and so yeah, we'll be back for the remainder installments of this series. All right. Okay. So see you in a moment. All right, and we are back. Let's see. So this question 2 of a series of 6. It says a piece of wire 8 meters long is cut into 2 pieces. All right. So let's kind of draw a picture here. So we got a wire. All right. And it's cut. So I'm just going to draw a cut. One piece is bent into a square and the other is bent into a circle. So I'm just going to call 1C for circle. Here, let's go in order. 1S for a square and 1C for a circle. So we want to maximize the area, right? So the total area. Okay. So okay. And the total distance is 8 meters. So then 8 meters from here to here. Okay. So then let's let x be the amount for the square. Okay. So then the amount we leave for the square, right? So then an equation for the area of a square based on x is going to be what? So if x is the amount left for the square, so what is that, x over 4? Squared? All right, because we cut it into 4 equal parts, then length times width. Okay. area of the circle is usually pi r squared, or the radius. Because we want, let me see. So the area of a circle is usually what? Pi r squared. So this piece, this C, is going to give us what? The circumference. Okay, let's go ahead and write the circumference of a circle. 2 pi r. Okay. So then C, another piece of information, is going to be what? 8 minus x. That's the amount that we have left for the circumference, right? Now, so is it possible to get the area in terms of C, or I guess in terms of x, right? Okay. So we can get, if C is the 8 minus x, that's going to be our circumference. We can set this guy equal to the circumference. And then we can get r in terms of x. Let's do that real quick and just see what happens. All right, C is 8 minus x, which is the circumference. So we can say 8 minus x equals 2 pi r. If we solve for r, 8 minus x divided by 2 pi. Okay. Then if we take this and plug this into the area formula for a circle, so then a of x, so the area of a circle in terms of x, should be pi times this 8 minus x over 2 pi quantity squared. So again, let me kind of recap that. If we let x be the amount left for the square, right? So then, well, that, I feel like that's not too bad, right? X is the amount left for the square. If we want a square, they have to have 4 equal sides. So then that means each side has a length of x over 4. So then the area of a square is length times width. X over 4 times x over 4 gives us that expression that we have. And then the area of a circle is pi r squared. This C at the top, this amount here, is what's left over after we use x. So that's going to be 8 minus x. The circumference of a circle is in general 2 pi r. So then if this is C, which is equal to the circumference, that's where this over here came from. And then if we solve for r in terms of x, we get this guy. And then take that and plug that into the area of a circle. So now we have the area of a circle in terms of x. We have the area of the square in terms of x. So then the area total, the total area in terms of x, is going to be, I'll write it as x over 4 squared plus area of a circle, pi r squared, yeah. We got this pi, and I need to simplify these guys, 8 minus x over 2x, sorry, 2 pi quantity squared, okay? Let me mute this. Okay. So now our goal, we want to maximize the total area. Let me see. It says how much wire should be used for the square, right? So that's our x. So we should just be able to solve for x, okay? So our goal is to maximize the area total in terms of x, okay? So again, the total area, let me simplify. We have this x squared over 16. We got this pi. We got this 8 minus x quantity squared over 4 pi squared. Okay. Let me do some cancellations here. This gets rid of one of those guys. Okay. So then what's our common denominator here? let me do it like this. The total area in terms of x. So if we want a common denominator, this over here needs a 4. So we're going to multiply this by 1 in the form of 4 over 4. So we'll get 16 pi on the bottom. This one we need to multiply by 1 in the form of pi over pi. So we'll get 16 pi on the bottom. Okay. So then if we account for these changes, on top we're going to have x squared pi plus 8 minus x squared. We need that 4. I'm going to put the 4 here in front. I might need to expand it out further. I was avoiding it, but over 16 pi. Okay. Let's expand it a little further. The total area in terms of x. Again, we got this x. We're going to rewrite that as pi x squared. I'm just putting the number in front. If I expand that guy, let me see, 64, 16x plus x squared, 16 pi. I'm going to distribute and combine like terms. So we got that 4x squared plus pi x squared gives us what? 4 plus pi x squared. Okay. 40 plus 24 is 64. So minus 64x. 240 plus 16, 256. Okay. Okay. So again, our goal is to maximize the area. So this is a parabola. Okay. So what? We basically we can take the derivative and then find the turning point, show that it's a maximum, right? Okay. So then let's look at A prime. Okay. Okay. So that first one, the 2 comes down. That's going to become what, an 8 pi on bottom. This 4 plus pi persists. We got our x. And then, what is that? They're both divisible by 8. 8. 16. Okay. What is that, a 5? No, 4. 40 plus 24. So minus 4, the x is gone. 4 over pi. And then the constant, that last term is gone. Okay. So essentially what I did that I kind of didn't say, I kind of rewrote each of these coefficients. Like the first one was 4 plus pi over 16 pi times x squared. So then the 2 came down. I simplified. It turned into 8 pi. That's where that came from. The second one was a negative 64x over 16 pi. 64x over 16 pi. Right? When I take the derivative, I'm just left with negative 64 over 16 pi, which reduces down to 4 over pi. And then the last one is a constant that when you take the derivative goes to 0. All right, the derivative of this guy goes to 0. Okay. So then what we should find our critical numbers. Any x that makes this either 0 or undefined. So we're going to set it equal to 0 and solve. So we add, we get this 4 plus pi over 8 pi x equals 4 over pi. So then ultimately x is going to be equal to 4 over pi. We got this 4 plus pi. We got this 8 pi. Okay. We need to simplify. So these are going to cancel. As far as 32. So that's like an exact result. That's our critical number. So we're saying that to finish the first derivative test, we should like do a test on either side of this number. Let me see what number this is approximately equal to. Okay, so let me see, 32 divided by 4 plus pi. Okay, so about 4.48. So that's approximately 4.48079. Yada 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 is more, but okay. So then we need to, like, if we finish out the first derivative test, we choose a number on the left, like basically like if we do like this, say this is our positive x, say I'm just going to call this, or this is our 4 point something, 4.48, yada yada. If we choose so if we compare this to what, the f prime or a prime, this should give us a 0 in the first derivative. All we need to do is show that on the left side of this, the a prime is increasing, on the right is decreasing, so that means that this is a maximum, which is our desired result. So an easy number to test would be 0 into a prime. Okay. So if we plug a 0 in, when x is 0, we get a negative result, right? This guy is gone, we get a negative result. So on the left, oh, wait a minute, that sounds like a minimum. Do we want a minimum? We want to maximize. Did I miss a negative? I think I did lose my negative. No, that was fine. Let me check again. If you add that, that becomes that. So then x equals 4 over pi, 8 pi, 4 plus pi. That's gone, that's 32, everything is positive. I think that's fine. 64. What about that guy? I'm getting a minimum value. We want to maximize to minimize the total area. Oh, okay. So we can get there is a minimum, but there is no max. Okay, that's probably why that's happening, right? So you see that the 0. Okay. So let's keep going, right? So we're getting that this is a minimum, right? Because when we chose a number on the left, we got a negative result here, which means the original was decreasing. On the right, a number on the right would be something like if we plug in 5. Let me see, when x is 5, it should be negative. Okay, I might have to calculate it. So then if we do 4 plus pi divided by 8 pi, okay, I'm going to say times 5, because I'm just choosing some number to the right. Then I'm going to say minus 4 over pi. Okay, we should get a positive result when we do. Okay, so that means that all the numbers to the right. So when we tested a number on the right side of this critical value, we got a positive result, which means the original is increasing. These two pieces together imply that this is a local minimum value, because it's the original. This says that for this critical value, the original function is decreasing on the left and then increasing on the right. So that means that this is a minimum value at this value of x. Okay. So then, if that's a minimum, let me see. So if we want to maximize the total area, there was no max, all right? But if we wanted to minimize the total area, we did get a minimum value. And for the square, we got x 4.48. Why is that wrong? Okay. Oh, they might want an exact result. That might be why they marked it wrong. And so the exact result would be this guy here. So I think the answer was correct, but they just might want an exact result, which they'll do that at times. So then just go with this guy here in purple, or at least just try it and just let me know if it does or does not work. Right? That's interesting. That was fun. Okay. So I got the same result. I got the 4.48 like you did, but I think they wanted an exact result. So then maybe try this guy here. Okay. All right. Let me see if I can get. No, that one was a little bit extensive. So we'll just kind of go with this result that we have. Okay. All right. And so with that, we're going to go ahead and end the session here, and we'll be back momentarily for the next installment. Take care. Peace. See you in a few. All right, greetings YouTube, Beautiful Mind here, and we're back with our third installment for this series of 6 questions. Let's see, so I'll do my best to just read this one. The print is kind of small. It says a farmer wants to fence an area of 6 million square feet in a rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. Let y represent the length in feet of a side perpendicular to the dividing fence, and let x represent the length in feet of a side parallel to the dividing fence. Let f represent the length of fencing in feet. Write an equation that represents. Okay. So this has several parts. Fencing an area of 6 million square feet in a rectangular field. Right. So we have our rectangular field. And so the area, 6 million square feet, and divide it in half with a fence parallel to one of the sides of the rectangle. So we got a fence, we want to cut it in half. That's going to be our fence. Okay. Let y represent the length and feet of a side perpendicular to the dividing fence. So we'll let this be our y over here. And let x represent the length and feet of a side parallel to the fence. And this will be our x. So let f represent the length of fencing in feet. Write an equation that represents f. A farmer wants to fence an area of 6 million square feet and then divide in half with the fence parallel. Okay. So then f of x. Okay. Wait a minute. F in terms of x. Okay. The length, so basically the perimeter, right? So, okay. So now, ultimately we want to get f in terms of x, but for right now, the total fencing, right, x occurs 3 times, so 3x plus 2y, right? Because we got a y over here, this is x, and this is x, okay? But we need to get x in terms of y. I mean, we need to get f in terms of x, and so we still have that y. So we do need to get y in terms of x. We have another equation with the area, right? The total area of this is 6 million square feet. So then we should be able to use that, right? So area of a rectangle is length times width, which is just x times y. Should equal, I'm just going to leave it as 6, but we got to keep in mind that this is in terms of millions, right? So then ultimately, y equals 6 over x, okay? So then if we want to get f in terms of x, 3x plus 2, and we do the substitution for y, is going to be 6 over x. Okay. Okay. Let's simplify this. So at this point, again, we left off with, we got this 3x plus 2 times 6 over x. Six times 2 is what, 12? X squared. So 3x squared plus 12 all over x. Okay, I think this is good. Okay, so this is our expression of the fence in terms of x, and this should be millions of feet, I think. That sounds like a lot, but I think, yeah, it says million, so. Write an equation to represent f in terms of the variable x. So we got this result here. I'm going to highlight it in purple. Let's see. Then find the derivative of f prime. Okay. I mean, of f of x. So then f prime. I think I'm going to go back to the way I had it before. I feel like that'll be easier to take the derivative of. So we got this 3x, or in other words, we want to find the derivative with respect to x of, that's going to be what, 3x plus, I'm going to write the second one as 12 times x to the minus 1. I feel like this form is just the easiest to take the derivative of, versus if we use the part in purple above at the top of the screen, we have to use like low d high minus high d low over low low. I just didn't want to do all of that. All right. Okay. So then if we keep going, derivative of 3x is 3. That derivative for the next term, the negative comes down, and we subtract 1, it gives us this. Okay, so this can be our f prime. If they don't accept that result, then maybe try 12 over x squared, okay? But either the black one or the blue one. Just, you can try the black one. I mean, it should accept both because they mean the same thing, okay? So that's f prime in terms of x. Find the critical numbers of the function. So that's going okay. The critical numbers are going to be any value of x that makes this guy either 0 or undefined. So I don't think we can, if we set it equal to 0 and solve. All right. If we're going to do the 0, I think we need to change the form. That's a 4 square root of 12. Well, we know that 0, right? Because usually it's any x that makes this function either 0 or undefined. So in this form, we see that when x is 0 is a critical number. Let's rewrite this guy. Okay. So so we have this f prime of x. So what I'm going to do is rewrite it in the following way. We're going to have this, 3x squared minus 12 over x squared, right? Basically, I got a common denominator and got it into this form. 3, okay. So now from here, our critical numbers are going to be any x that makes this guy equal to 0, or it makes this undefined. In other words, any x that makes the numerator 0 or the denominator 0. So we got to basically do multiple cases, right? So if we set the numerator to 0 and solve, so then x equals, what is that, plus or minus 2. But I think in this context, the negative result doesn't make sense, right? So in this context, we're going to just get rid of the negative because we're dealing with, it doesn't make sense to have a negative result here. So we're just going to go with x equals 2, right? So that's part of the reason why I changed the form, because it was kind of easy to miss this other 0, this other critical value or whatever. So that's from the numerator, and then from the denominator, again, just x equals 0. I'll say or. And again, I think that in the context of this problem, x equals 0 doesn't make sense in the context. Okay, so I'm actually gonna exclude this guy. It might be a result, so I'm gonna leave it on the screen, but for the context, I'm gonna not use it. So then our goal to minimize the cost of the fence. Okay. So let's minimize the perimeter, because we want to fence in the total area, but we want to minimize. I think let's minimize your f. Okay. So this is our critical value. We need to show that this is a minimum value. So this is our x. This is our 2 million. And we want to compare this to f prime. Right? And the derivative of this guy should give us a 0. Yeah, it does. Okay. And then we need, so a number on the left, an easy number on the left to test is like when x is 0. All right, when x is 0, well, no, we can't do that one. Let's test, because we can't do x is 0 because it gives us a 0 in the denominator. Let's test when x is 1. If we plug a 1 into the derivative, on top we get a negative value, on bottom we get a positive. That means the overall thing here is negative, right? So that's a good omen. So when we chose the test value on the left here, we got a negative result, which implies the original function is decreasing on the left side of this potential critical value. And then a number on the right to test would be something like 3. If we plug 3, 9 times 3 is 27, we get a positive number on top, positive number on bottom,
So then ultimately, this guy is positive, right? So we chose a number on the right. We got a positive result, which implies the original function is increasing. Those two pieces together imply that this is a minimum, a local minimum. Right? At this x value, okay? And then, so when it says the critical number, they might accept either 2 or you might have to write out 2 million, right? So for this critical number, either put 2, but you might have to put, I'll do this in green, I'll say, or you might have to write it as 2 million. Okay. Feet. What should be the length of the sides in a rectangle in order to minimize this? So when x is 2, right? Smaller. What should be the length of the sides of the rectangle of the field? Where's y? Okay. If x is 2 million, y would be 3 million. So 2 million feet and 3 million feet. So it looks like we're getting 2, and it should be either 2 million or just put 2. Let me see my units here, because it just says feet. That's why I'm writing out the long number. I'm thinking it's 2 million feet and 3 million feet. That's crazy. These are the results that I got. And it might just be 2 and 3, but let me see. Okay. So the total area, 2 times 3 is 6. All right, 6 million feet. We didn't necessarily find the minimum cost, but we could. Basically, the minimum perimeter. Anyway, okay. So that one was a little bit, it wasn't too terribly bad. I'm not getting the whole thing here, but that's okay. All right. So we're gonna go ahead and end the session here, and we'll be back momentarily for the next installment. All right, take care. Peace. All right. So greetings, a beautiful mind here, and we're back with the fourth installment of the series of 6 questions from calculus. And this question says, a rectangular storage container without a lid is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs $15 per square meter. Material for the sides costs $9 per square meter. Let W denote the width of the base. Find a function and the variable W giving the cost of construction of the box. So we want to find C of W. So we want to find the cost based on the width. Let's start with an image.
I knew there was something simple I could do. That's decent. Okay. Okay. So the dashed lines means it's like you're looking through the image, right? Okay. That was an adventure. Okay. So a rectangular storage container without a lid is to have a volume of 10 cubic meters, right? So the volume here, 10 meters cubed. The length of the base is twice the width. So L equals 2W. Okay, so I'm going to let this be my L down here. L equals 2W. And this is my W here. So W Sorry, I know I'm being a little quiet. I'm drawing. So W So W is the side, L is the bottom. I just did the bottom for L because it seemed like it was twice as big. Okay, let's keep going. Twice the width, okay. Material for the base. So I'll just kind of, material for the base is $15 per meter squared. Materials for the side is $9 per meter squared. Let W denote the width of the base. So we want to find the cost in terms of W. So per meter squared, right? That's an area. So we need to find the base in terms of W and the side in terms of W. Okay. Per square meter. So the base, we want to find the base in terms of W. Length times width. So there's going to be length times width. So there's going to be 2W times W. It's going to be 2W squared. So then that's going to be what? Square meters. So then if that's the base, we're going to say that times 15. So then the cost of the base in terms of W is going to be what? 15 times 2W squared. Okay. Now the height, now we have that the volume is 10 square meters. So the volume would be what? Length times width times the height. Okay. So then that would be what? 2W times W times the height equals 10 cubic meters. Okay. So then our height is going to be 10 divided by 2W squared meters. Okay. So then the total, let's just go ahead and try to find the total area of the sides, or the cost for the sides in terms of W, right? Now that left side, the area would be what? The width times the height. So the width times the height. But then we have two of those, right? That occurs twice, the left and the right. So we're going to say times 2. So this is the left and the right. I'll just note it here. This is for the left and the right. That's where this comes from. Okay. And then, so that, oh, well, if we want the cost, well, the whole thing we're going to have to multiply by 9. We'll get that in just a moment. So then the front and the back, so we need to say L times H, right? Okay. So again, it's going to be 2 of those. Our L is 2W. Our height is 10 over 2W squared. This comes from the front plus the back. Okay. And this is the cost of the side. So because it's the side, we need to multiply this total area by 9. Cost of the side in terms of W is going to be a 9 times, let me do my simplification. So these 2's are going to cancel. This cancels one of those guys. So then we're left with the 10 over W there. Okay. This 2 can cancel that 2. This W can cancel one of those. 20 divided by W. So then the cost of the side in terms of W $30. 9 times 3 is 27. Dollars. So this was the cost for the side. This is dollars. This is the cost of the base. Okay. So then the total cost in terms of W, that base, all about that base, dollars, 30W squared. Okay, so I got that for the total cost. Find the derivative, find the costs for the least expensive, so we want to minimize the cost. Okay. Okay. So then C prime right back, guys. I think I'm gonna just call her back. I'm almost done. Oh, let me call her back.
Okay, give me. You say I should have got this.
Hey, can I call you back?
I've got a salesperson here trying to help me to buy the right.
Okay, sorry about that. So we are back. Let's see. So this is the cost we got in terms of W. So now we want to find C prime, the total cost. We want to find C prime, the derivative of the total cost in terms of W, right? 2 comes down, 3 times 2 is 6, so that's a 60 W minus 270 W to the minus 2. Okay. Okay. So then the derivative of the total cost in terms of W so there's going to be 60 W cubed minus 270 all over W squared. Okay. We want to find any W that makes the numerator 0 or the denominator 0. So if we set the top to 0 and solve, okay, so so we get W equals the cube root of 9 over 2, or 0. Okay. Again, in this context, we wouldn't really use the 0. And cube root of 9 over 2 6596. Okay. Meters. Okay. So we found our derivative. That's going to be the least expensive. Okay, so we need to verify that this is a minimum. Okay. Say this is our 1.65096. Okay, a number to the left to test. Again, we should do 0, but I'm not going to do it here. A good number to test on the left would be something like 1. Well, we should put 0 so that way I'm just going to go with this one for just for the sake of time. Because again, 0 doesn't make sense in the context, but you do need to be aware. Like, because if we had chose a negative number, that's going to be on the other side of that critical number. It would throw things off. I mean, to be thorough, we should do like a 0 here. Like, for instance, if we plug in like -1 into the derivative, if we plug in -1, this would be negative. So the top would be negative. This would be a positive. So that whole thing would be negative in that region. So in region A, we got a negative result, which implies the original. See, that's getting thrown off. Let's just keep going with it. That implies the original is negative over there. In region B, a number to test would be a number like 1 into the derivative. If we plug a 1 in, we get a negative result, and that's fine. All right. We get a negative result here, which means that the original is decreasing in region B. Okay, that's fine. Because it might be something like an S, and then the minimum is our critical value. A number in region C to test is something like when W is 2. We know the bottom is positive. 8 times 6 is, dang, is that negative? Oh, no. 8, no, it's not negative. 8 times 6 is what? 48, so 480 is positive, right? So then ultimately the derivative is positive in region C, okay? So that implies that this is a local min at this value, so at a critical value, okay? So the cost is minimized for W equals, okay? Let me kind of create a little bit of space. And let's do orange. So we got, well, it's minimized for this W, but we need to find the minimum cost. So we need to take that W and plug it back into our cost function. Cube root of 9 over 2. Okay. So then, again, we want to take this W and plug it into that function. So what I'm going to do, does it want an exact result? It might want an exact result. Okay, just in case it wants an exact result. So the total cost, I mean, that doesn't make sense. If it wants an exact result, just let me know and I'll come back and find it. I'm just going to plug it in to get a dollar approximation. So I'm going to go to my y equals, we got 30x squared plus 270 divided by x, okay? I want to evaluate this function when x is 9 over 2 to the power of a third. The minimum cost, let's go to 9 over 2. Insert a 2. Dollars. So the total cost, and that's the minimum. Does that make sense? $245.32. I just took the ceiling to cover it. Because if you put 31, you might be short of it. It's either 30, 31, and 32. 245 minimum cost. Is that right? Nearest cent. Oh, okay. So it says round to the nearest cent. The nearest cent would be 31. Okay. Yeah, that's about the best we can do. So just let me know again. If it doesn't work, just let me know and we'll come back and correct it. Okay. And so with that, we'll end the session here and we'll be back momentarily for the next installment. Take care. Peace. All right. And we're back. So, beautiful mind here. This is question 5 of a series of 6, the 5th installment of a series of 6 questions from calculus. And this one says to find the points on the ellipse 5x squared plus y squared equal to 5 that are furthest away from the point 1 comma 0. Okay. So let's see. So if we think of the ellipse, right, just like, if we think of the ellipse, every point on the ellipse, like if we want to like capture all the points on the ellipse, they're going to take on the form of x. Any x that you choose, y is going to take on a certain form. So what we're going to do is take this equation for the ellipse and go ahead and solve for y. Let me see. So if we have 5x squared plus y squared equal to 5, if we solve for y, y squared equals 5 minus 5x squared. Okay. So then y equals what? Plus or minus the square root 5 times 1 minus x squared. Okay. So I guess the short answer. So for every x that you have on the ellipse, the y is going to take on the form plus or minus, and these are really 2 ordered pairs. Plus or minus the square root of 5 times 1 minus x squared. Okay. So that's how we capture all of the ordered pairs for this ellipse. So then the distance formula, distance between 2 points, P and Q, right? The distance between 2 points, x2 minus x1 squared plus y2 minus y1 squared. Okay. So given 2 points, the distance between those 2 points, and we want to maximize the distance. So our goal is to maximize the distance between x and y. And we want to compare this to the point, what is it, 1 comma 0? So we might have to do it a couple of times because of that plus or minus. XY, XY. Okay. So for my x's, my x2 minus x1, I'm going to say 1 minus x, quantity squared, plus, it would be, if I did the negative first, it would be 0 minus the square root, so double negative would become positive. And then the squared would cancel it. It would be the square root of 5 times 1 minus x squared, and then the quantity squared. Wait a second. Whether it's plus or minus, it seems like it would collapse, right? Because if you have the minus, once you square it, it's gone. If you have the positive, once you square it, it's gone. So I'm just going to, it looks like the plus and minus gets absorbed, and it really becomes the absolute value. When you square root, I want to say, well, actually, if you take the square root of something squared, that's absolute value. But in either case, the square root is gone. We're going to be left with 5 times 1 minus x squared. This square root persists, right? Because when we square, because of this square here, it got rid of the plus, it got rid of the plus and the minus and the square root, right? So that's why I just did it in one go like this, okay? So our goal is to maximize this distance. Now it looks like we can simplify this, right? Because we got one of something. Okay, well, that's squared. No, it's not. It's not. We can't combine these. What we can do is expand the radicand, the part on the inside, and then see if we can find a perfect square. Let me expand and combine like terms. Just let me try to simplify it some. So again, our goal is to maximize the distance between any 2 points. If we expand the first guy, 1 minus 2x plus x squared. If we distribute that 5, it's going to be 5 minus 5x squared. Now if we combine like terms, one minus 5 is a negative 4. Negative 4x squared minus 2x plus 6. So I don't think it's can this be factored? We could factor out a 2 from everything. But I don't think it's a perfect square. We might be able to factor it, but it's not a perfect square. So from here, if we want to maximize this distance, we need to look at the first derivative, and we need to find the critical value, show that that critical value is a maximum. So if we can take the derivative, find the critical value, and show that that critical value is a maximum, then we can finish this guy. Okay? So then d by dx of this function, the 1/2 comes down, inside persists, that's going to be to the power of a negative 1/2 times the derivative of the inside function, negative 8x minus 2. Okay, let me kind of rewrite this. I'm just going to write it as d prime. I probably shouldn't say x and y. That should say between 2 points. I'm going to just call it p and q. Those all need to say p and q. Because we're not, that x and y is in the proper nomenclature. Okay, so distance between 2 points, that's fine. Okay, so now on bottom we have this 2 times the square root top, we got this negative 8x minus 2, okay? And then our critical value is going to be any x that either makes the numerator 0 or the denominator 0. So from the numerator, if we have a negative 8x minus 2, we set it equal to 0 and solve. Add 8x and divide. X equals a negative 1 by 4. So if we could find the x that makes the denominator 0, all we would really need to do is set that radicand to 0. So if we could find like this negative 4x squared minus 2x plus 6, we want to set that equal to 0 and solve. Can this be factored? We can divide out, what, a negative 2 from all the terms? That'll give us 2x squared plus x minus 3 equal to 0. Okay, so if we want to factor this guy, we're looking for two numbers that multiply to give us negative 6, add to give us 1. What is that? 3 and negative 2. Okay. So then I got this 2x squared. I'm going to rewrite that 1x as minus 2x plus 3x minus 3 equal to 0. Got 4 more terms. I'm going to do my factor by grouping. We can factor out a 2x, and we're left with x minus 1. The goal is we're really looking for an x minus 1 over here. We can factor out a 3. That leaves us with x minus 1 equals 0. So then ultimately we get x minus 1, 2x plus 3 equal to 0. So then from there, our critical numbers that we get, negative 3 by 2 and 1. Okay. So what's this context here? So these points, okay, so we got 3 critical numbers. Here's our d prime. Not seeing anything immediately. So yeah, okay. So this negative 1 by 4, this negative 3 halves, and this 1, we need to do our first derivative test. Okay. So this is our positive x. Okay, so say this is our negative 3 halves. Say this is our negative 1 by 4. Right, and then this is our 1. Okay. This one makes, so, and then if we're going to consider, is it f? Or d prime? Let's see. This one makes d prime undefined. This one makes d prime 0. This one makes d prime undefined. Okay. So then these candidates break the number line up into 4 regions: A, B, C, and D. Okay, let's see. So where's our first derivative? Okay, let me just zoom out. Okay. So a number in region A to test would be something like negative 2. If we plug negative 2 into our first derivative, it looks like the numerator is positive. Let me see, if that's a negative 2, that's going to be what? Negative 16, negative 10. Looks like the denominator is going to be a negative. So the whole thing ultimately is going to be negative in that region. So I got that the first derivative was negative here, which means the original is decreasing in that region. A number in region B to test would be something like -1 into the first derivative. If we plug -1 into the first derivative, the top is positive. 8. Looks like the bottom is positive. Oh wait, we can't take the square root of negative, so is the bottom always going to be positive? We chose -2 there. 10. Yeah, positive. Uh-oh. Yeah, because we can't take the square root of a negative. Okay, it looks like the bottom might always be positive. I forgot about the square root when I did it before. It looks like this guy was positive. Let me test -1 again. That's positive and that's positive. This should be positive. So I'm going to positive first derivative, so it's increasing there. We can test 0 in region C. If we plug in a 0, that's positive, and that's negative. We get a negative, which is what we wanted. Okay. And then 2, we should get a negative. Are we trying to maximize them? Yeah, we should get a negative. I mean, let's just see. So if we plug a 2 into the first derivative, that's negative. That should be positive. So it should be negative, right? Okay. So we only had a max when x was -4, right? Again, this implies that this is our local max when x is a -4. And we found y in terms of x. Yeah. Okay. So our claim is that the distance is maximized when x is a -1/4. Maximum distance, so basically the plus or minus. So then back in the original, we got the -1/4. Okay, I think we just need to evaluate it properly. Right there, okay. So we want the max distance right here. Let's copy, paste, okay. So when x is a -1/4, then our y is going to be plus or minus square root 5, 1 minus 1/16, positive. So then 16 minus 1 is 15/16. 15/16. 50 plus 25 is 75/16. (25 times 3). So 5. Looks like it's 5/4 times the square root of 3, plus or minus. And that might be, they probably wanted an exact result. Oh, you put 2 instead of 4. Wow. Yeah, I got 4, right? Square root of 16 is 4, not 2. Wow. Plus or minus 5 over 4 times the square root of 3. I think you have 5 over 2 times the square root of 3. That's crazy. Yeah. So right here, I think that's supposed to be a 4. And that's supposed to be a 4. And then I think everything else is good. Wow. Let me highlight my result. That was an adventure. So we got a negative 1 over 4, comma, negative 5 over 4 times the square root of 3. And then we got a negative 1 over 4, positive 5 over 4 times the square root of 3. At least we're getting the same results. This is what I got. I mean, shy of that too. I just think that somebody like, you know, it was supposed to be a 4 instead of a 2. Wow, that was an adventure. Okay. So with that, we'll end the session here, and we'll be back momentarily for the final installment of this series of 6. All right, take care. Peace. All right, greetings YouTube. Beautiful Mind here, and we are back for the final installment of the series of 6 questions from calculus. I'll just read this one off. It says, if C of X is the cost of producing X units of a commodity, then the average cost per unit is C of X equals C of X over X. Consider the cost function given below. Round your answer to the nearest cent. Find the total cost in dollars at a production level of 1,000. So then there we should just plug in when X is 1,000. We got that 323,736.66. Matter of fact, let's just confirm that. What I'll do is hop over here and I'll go to my Y equals. We got this 24,123 plus 110x plus 6x to the power of 3 halves. Okay. Then I want to evaluate this when x is equal to 1,000. 2, 3. And we should get that 323,736.66 is good. Find the average cost. So then the average cost function is going to be C of X divided by X. So we divide this by 1,000. We got 323.74 per unit. That's good. The marginal cost comes from the derivative. So let's go ahead and find the derivative because I think we might need it to kind of fill in the blanks. If our C of X 24,000 plus 110x plus 6x to the power of 3 halves, okay? The marginal cost should come from the derivative. So that's going to be a 110 9x to the power of a half. Okay. So then what I'm going to do, I'm going to go to my math. I want option number 8 for the nth derivative. I want to take the derivative of that function that we just inserted with respect to x when x is 1,000. Okay, and we should get 394.60, and we do. Okay. Okay. Okay, find the production levels that will minimize the average cost. So C of X. So average cost was C of X over X. And our goal is to minimize the C of X over X, right? So in order to do that, we need the derivative of this function. So we need to find d by dx of this C of X over X, and then analyze it. Okay. So we're going to have this Now I feel like it would just be easier to just go ahead and divide each term by x. So we're going to have this 24,000 times x to the minus 1 plus 110. Let me see. Plus 6x to the power of a half. Okay. And again, we want to take the derivative of that. So d by dx of this. Okay. So now we're going to take the derivative there. We get a negative 24,000 x to the minus 2. That constant in the middle is gone. The 1/2 comes down, becomes a 3 x to the power of a negative 3/2. No, not 3/2. The negative 1/2. Okay. So then, let me see. We got these negative powers. Let me rewrite this guy. So that's a negative 24,000 over x squared. That's square root of x under 3. You would need to multiply, if that's to the power of a half, we would need to multiply, if we want a common denominator of 1, x squared, 3/2. So we're multiplying by 1 in this form so that we get both denominators to the power of x squared, right? So then we got what? 3x to the 3/2 minus 24,000 over x squared. Okay. So then we need to, our critical numbers are going to be those x values that make either the numerator 0 or the denominator 0. So from the numerator, if we set that to 0 and solve, we'll get this 3x to the 3/2 equals 24,000. X to the 3/2 equals 8,000. 2/3. Square both sides, right? So then x equals 8,000 to the power of 2/3. $400. Okay, so that's our critical number. We need to, what's our goal? We want to minimize this cost, $400. So then we need to confirm that that's a minimum value. So this is our positive x, and this is our 400. And it's $400. Number, and then 0 looks like it's another critical value. The number on the left to test, I would test like, let's do like 200. Let me see. Let's do an easier number like 100, right? Square root of 100 is 10 to the power of 3 is 1,000, so 3,000. So this is going to be negative. This is positive, right? That's a good omen. So then so this should be a 0 there. We got a negative result over here, which implies the original is decreasing. A number on the right to test in the first derivative. If I need a perfect square. So 9. Let's do 900. The square root of 900 is it not 3? 20. 20 times 20 is what? 400? What about 30 times 30? 900? So the square root of 900 would be 30 to the power of 3. 27,000 times 3. So ultimately it's going to be a positive over a positive, right? The whole point of that, we're just trying to get to the sign. Once you know, we don't need the exact number, we just need to know the sign. Okay, so then that implies that this is a local minimum at this critical value. Okay, so let's answer the question. So the production level, so what's the value of X? Oh, so that can't be dollars. That's not dollars. That's 400 units. That will minimize the cost. So I got 400. So then here, I got 400 units. And then the average cost, the minimum average cost, we plug 400. The average cost, okay. So I'm gonna just use the original. I'm gonna evaluate this function when x is 400. I'm gonna say divided by 400 because we want the average cost. It's 290, yeah, 290. Per unit, $290 per unit. Okay, that was an adventure. Man, these things really be adventures. Like I'll be going on journeys. You got to think about it, what makes sense, and then crunch the numbers. It'd be a lot. And yeah, yours was close, but you know how these programs are. They weren't exact, so there was probably some rounding along the way, but yeah. These are the results that I got. So just try them out. Again, with any of these results, if anything doesn't work, just let me know and I can go back and look at it and like revise it. Okay. All right. So with that, that concludes these series of 6 questions from calculus. I'm not saying they're all 100% correct. Again, you got to check them. If anything is off, you got to let me know. Sorry, I'm not sure if you heard that or not because I was totally yawning. But yeah, if anything isn't correct, just check them and let me know. I'll go back and look at them and try to revise them. All right, so with that, we're going to go ahead and end the session here. And from one beautiful mind to another, take care. Peace.